So let's go ahead with the lecture. So this is a link for further reading on the acidity and basicity. Okay, so this is if you want to read any more information about what we are discussing right now. So in the last class, this is what we discussed. That is how pH determines how much H plus will release. Okay, and that is then dependent on factor like pK. Okay, so pK being a constant, the variables here is the pH, or in other words, how pH is of how this relation, that is A minus by HA, this ratio is a function of pH. Okay, so this is what we know from this equation. So this is what we discussed in the last class. Also, what we learned is that how we discussed qualitatively and quantitatively how at different pH the acid dissociation is influenced. Okay, so that we learn from this picture as well as from this equation. Now, so there are some simple rules which you can use to apply this equation. So let's use the acetic acid as an example. So CH3COOH forming CH3CO minus and H plus. Okay, and as we know, the pK of this one is 4.75. So the pH, let's just find out what is the dissociation or ionization at three different pH. Okay, so just use we are using a term either dissociation slash ionization to describe this phenomena of HA being dissociated into H plus plus A minus. So this is called dissociation because this is dissociating into two forms. This is also called ionization because it is generating ions. Okay, so what we are measuring here is that at pH 3 and pH 4.75 and pH 6, what is the degree of dissociation or ionization? This particular column here is the ratio of CH3CO minus by CH3COOH, which you can calculate from this equation. So then this particular one is the representation of this information, and this is percentage ionization. So we'll come to discuss this. How can you calculate? Okay. So first, this is calculation. This one is simple. So if you rearrange this equation, it would become log 10 CH3CO minus by CH3COOH. Okay, so I misrepresented writing this, so let me just correct it a little bit. Okay, so the right way of writing this is this. So this is here, and more accurately if you put a bracket. Okay, log 10 base of this one. So if you do that and put the value of the pH into this, that is here, and the pK into this, it is here, we are going to get this three numbers. So at pH 3, this is 0.017. At pH 4.75, when pH equals to pK, it is 1. And with pH greater than pK, then it is 17.7. You can rewrite this as CH3CO minus by CH3COH, that is 17 by 1000 and 1 by 1 and 17 by 1. Or what you can interpret this as, out of, for each 17 molecules of H plus, which is the same as CH3CO minus, there are 1000 molecules of CH3COH, which is undissociated acid, meaning the acid is predominantly undissociated. Right? So we learned this earlier also. At pH 1, this ratio is mostly 1 to 1. Okay, this one molecule of H plus, there are one molecule of undissociated acid. Undissociated acetic acid. For this one, that ratio becomes for one molecule, for 17 molecule of H plus, there are one molecule of undissociated acid, meaning it is predominantly dissociated or ionized. Right, so you learned this earlier also, that an alkaline solution, why this is happening. So what you can tell is that at pH, when the pH is less than pK, right, so pK here is 4.71, right, so when the pH, which is 3 and it is less than pK, you can say that the ionization is not so much and it is less than 50%. When it is equals to pK, it is 50%, and when it is more than pK, it is over 50%. Okay, so that is something we are learning from this. Okay, so you can also use this ratio to calculate the percent ionization in a quantitative manner. Okay, so I'll just go to a new slide and calculate it. So how you can do it is, let's just take the first example. At pH 3, what is the percent ionization? So what is the percent ionization? So in this equation, what percent of CH3COOH has dissociated into H plus? Meaning what percent of total CH3COOH has dissociated into H plus. Okay, so let's find out that. So let's just take this ratio again, that CH3CO minus by CH3COOH is 17 by 1000. Okay, so what I'm going to do, because CH3CO minus, in this case at least it is the same amount as CH3H plus, so I'll just rewrite this as H plus by acetic acid concentration would be equals to 17 by 1000, meaning out of every 1000 molecule, for every 1000 molecule there are 17 of H plus. So how I can calculate the ionization ratio? What I'm going to do, see, this 17 H plus must have come from this CH3COOH. So if I add them in the denominator, that would give me that how many originally CH3COH was there. Okay, so see, before this all happened, at time equals to 0, there were 100 molecules of this and 0 molecules of this. So when it reached equilibrium, it became roughly like 17, 17 and 1000. Okay, so this is initially 100%, this was 0%. Now right now it is 17, each of this is 17 and this is 1000. So if we trace back the time, we can get the original number. Okay, so how we are getting this? We are dividing the H plus by H plus into this. Okay, so this must be representing the how many originally CH3COH was there. So that would be 17 by 17 plus 1000. Okay, so if you calculate this, this is going to be, give me 1 second, this is going to be 17 divided by 1017, or more specifically 0.016, which represents 1.6%. Okay, so this is a dissociation being 1.6%. Similarly, you can calculate the dissociation here. It would be 50% because this is 1 by 2. So 50%, and this is, if you calculate, this is close to 99, over 90%. Okay, so that is where we get the percent dissociation from. So the rule of thumb here, if the pH is less than pK, you are getting less than 50%. If the pH equals to pK, that is 50% ionization, and if the pH is over pK, that is more than 50% ionization. Okay, so this is something you need to remember. So what is the effect of this on the amino acid ionization? So amino acids have various kinds of side chains. So arginine, for example, has an alkaline side chain or basic side chain, which is this one is protonated, and this is the side chain pK. This pK is for its COH, main alpha COH. So what is alpha COH? So this is the backbone structure, basic backbone structure. Okay, and this is the R group. Okay, so this pK is the alpha COH. So why is it alpha? This carbon contains all the both the amine and the this carboxyl. So in chemistry nomenclature, you call this alpha based on because this is associated with the primary functional group. If the next carbon is there, that would be beta. Then third carbon would be gamma, and so on. Okay, so this is the alpha COH. Then this is called alpha NH3. This is the pK for those. Okay, so this being 2.17 and 9.04 for arginine. Okay, the side chain is 12.48. Similarly, aspartic acid has an acidic side chain that has a considerably low pK, and so on. So all the pKs is provided. Okay, so you can it gives you an idea of how the some of the amino acids are acidic, some of them are basic. For example, arginine, you can say that pK is so high. Arginine pK is so high, it is a base. But aspartic acid pK is low. Okay, that is, I'm talking about the side chain again. Okay, remember, I'm just talking about the side chain. pK is low, so it is acidic. Okay, so one more example, let's look at. So cysteine, for example, this is on the more on the alkaline side of the side chain. Okay. So another one, histidine, it is more on the neutral side, but still would be considered a little basic. Okay. There is glutamic acid, that is a more on the acidic side of the side chain. Okay, so that is that. Okay, and this particular column is the structure of the side chain when it is completely protonated. So what does this numbers mean? So this numbers mean is that this determines that depending on their pK, this side chains will ionize at different pH. So let's just take an example of aspartic acid. This is aspartic acid here. So aspartic acid, these are the three pKs. pK1 is 1.88. This is alpha COH. pK NH3 plus is 9.68 and pK2 is 3.7. Okay, so this asks this question: which acid groups will predominantly, that is over 50%, ionize at pH 1.5, pH 3, pH 4, pH 8 and pH 10? So we can calculate this quantitatively using the Henderson equation, or we can use this shortcut which we learned in this slide, that if the pH is less than pK, it will ionize less than 50%. If the pH equals pK, it is ionized 50%. And if the pH is over pK, it will ionize over 50%. Okay. So let's use that rule here. So that is the rule that I was just discussing. So the first acid chain is the acid 1, which is this one, which is alpha COH. Acid 2 being side chain COH. And acid 3 being alpha NH3 plus. Okay. Now at pH 1.5, the pKa is less than 1, both 1, 2, 3. See, pH 1.5 is less than the pK of this one, less than the pK of this one, obviously, and definitely less than the pK of this one. So none of the groups will ionize more than 50%. Okay, and this is the actual calculation of it. But if you want to summarize, so none of the groups will ionize more than 50%. At pH 3, okay, next one we want to consider the pH 3. We just considered this, we want to consider pH 3. At pH 3, it is just over pK1, but still less than pK2 and pK3. Right, so pK1 will ionize more than 50%, but these two are still less than 50% and less than 50%. At pH equals to 4, this is over the pK of 1 and 2. So pK1 is this one, pK2 is this one. So this will ionize over 50%. This will ionize over 50%. But this is still less than 50% for this one. pH 8, it is over the pK of this one and this one, that is pK1, pK2. So this will ionize over 50%. This will ionize over 50%. But as pK3, that is NH3 plus groups, it will still be less than that, for less than 50%. Now at pH 10, it is over the pK for all three. So now for all three, it will be over 50% ionization. Okay, so we just use this rule to interpret. And more quantitatively, this is the ratio that you can calculate out of this. So the ratio being the A minus by HA, or in other words, H plus by HA. Okay, that you can calculate for all three acid groups. Okay. So what is the implication of this? The implication of this is that depending on pH, various acid groups will ionize at different extent. That, I will show in the next slide, will determine the charged state of this amino acid, and in some cases it will be positive, in some cases it will be neutral, and in some cases it will be negatively charged. So let's look at that. Okay, so that is the same calculation. So at pH 1.5, we know that none of them will ionize, so all three are less than 50%. So this is their structure. Well, this is not ionizing, this is not ionizing, this is not ionizing. So if you look at the net charge of this molecule, this is neutral, but this is +1, so net charge is +1. At pH equals to 3, it is over the pK for this group, but not so much for the other two. This is still less than 50%, so those will not ionize. Okay, so this is not ionizing, this is also not ionizing. Now this case, the net charge is neutral because plus and minus, they're cancelling each other, and we call this the Zwitter ionic form of the amino acid. So each amino acid at some stage has a Zwitter ionic form. At pH 4, this is over 50% for this one and over 50% for this one, but not so much for this one. So this has now negatively charged. This should also be negatively charged, but this is still +1. So overall, it's a net charge of -1. At pH 8, again, this is still over 50%, this is over 50%, but this is still less than 50%. So still the net charge is -1 because this is minus, and this is plus. At pH 10, now all of them are over 50%. Meaning that the net charge has now become -2. Right? So that's how it controls the charge of the pH. So as I said earlier that you can use either the buffer or the protein microenvironment to control the pH, and that way you can control the charge of the molecule. Okay, so that would be playing an important role in the enzymatic activity. Another important point is that in this particular range, somewhere in this particular range, the molecule will have a neutral form. So that is called the zwitterionic form. The solution will be neutral. Okay. So that particular pH is called isoelectric point. The pH at which the amino acid is completely neutral, or the solution is completely neutral. Okay, so I'll stop here